In this video, we will be learning about equilibrium state and equilibrium in physical processes. We will be seeing what we mean when we say we have to establish a particular equilibrium in a particular process. We will also see what the state of equilibrium actually means.
Equilibrium. We are all familiar with the game tug of war. In this game, a situation arises when both the teams pull the rope with full power and vigor, yet the rope does not move in either of the directions. This state is actually an example of equilibrium. This condition normally occurs when the team members of both the teams are applying equal force. Bringing another person in any one of the teams disturbs the state of equilibrium. Similarly, equilibrium occurs in various physical and chemical processes when no change in the concentrations of various species in the reaction mixture is observed. Come, let us discuss this topic in detail in the module Equilibrium. After reviewing this digital content, the students will be able to analyze dynamic nature of equilibrium involved in physical and chemical processes, state the law of chemical equilibrium, write expressions for equilibrium constants of homogeneous and heterogeneous equilibria, establish a relationship between Kc and Kp, describe briefly the various applications of equilibrium constants, explain various factors that affect the equilibrium state of a reaction, explain Arrhenius, Bronsted, Lowry and Lewis concepts of acids and bases, classify acids and bases as weak or strong in terms of their ionization constant, understand the dependence of degree of ionization and concentration of the electrolyte and that of the common ion, describe pH scale for representing hydrogen ion concentration, briefly explain ionization of water and ionic product Kw of water, appreciate the importance of buffer solution, calculate solubility product constant.
In this video, we will be learning about different types of equilibrium. Basically, equilibrium between different states of matter. For example, solid-liquid equilibrium, liquid-vapor equilibrium, and solid-vapor equilibrium.
Equilibrium state. It is usually observed that many chemical reactions do not proceed to completion when they are carried out in a closed container. This implies that the reactants are not completely converted into products. Instead, after some time, concentrations of the reactants do not undergo further decrease and the reaction appears to have stopped. This state of the system in which no further net change occurs is called a state of equilibrium. The given reaction is an example of process attaining equilibrium. The double half arrows indicate that the process in both the directions are going on simultaneously. The mixture of reactants and products is in the equilibrium state is called an equilibrium mixture. Equilibrium in physical processes. The equilibrium involving physical processes are referred to as physical equilibria. The physical equilibria involving change in state are of three main types. These are solid-liquid equilibrium, liquid-vapor equilibrium, and solid-vapor equilibrium. Let us discuss these types one by one. Solid-liquid equilibrium. When a solid-liquid system at melting point is taken in a well-insulated container, then this constitutes a system in which solid is in dynamic equilibrium with liquid. For example, when ice and water at 273 Kelvin are taken in a perfectly insulated thermos flask, the temperatures as well as the masses of ice and water remain constant. This represents a dynamic equilibrium between ice and water. Since there is no change in the masses of ice and water, the number of molecules going from ice into water is equal to the number of molecules going from water into ice. Thus, at equilibrium, the rate of melting is equal to the rate of freezing. For any pure substance at atmospheric pressure, the temperature at which the solid and liquid phases are at equilibrium is called the normal melting point or normal freezing point of the liquid-vapor equilibrium. Let us consider evaporation of water in a closed vessel. When a small amount of water is taken in an evacuated vessel at room temperature, it starts evaporating. This process continues for some time, as indicated by a gradual decrease in the level of water. After some time, it is observed that the level of water becomes constant, indicating that no more water is evaporating. This indicates that a state of equilibrium has attained between water and water vapors. The equilibrium seems to be static, but in actual practice, it is dynamic. In the beginning, the rate of evaporation is more, and hence the water vapor concentration increases, which in turn condenses back into the liquid. As the concentration of water vapor increases, the rate of condensation also increases. At equilibrium, the rate of evaporation is equal to the rate of condensation. Liquid vapor equilibrium can be illustrated by taking a small amount of water at room temperature in an evacuated vessel attached to a manometer. Due to evaporation of water, a pressure is developed in the vessel and the mercury level in the manometer rises gradually. The mercury level in the manometer becomes steady after some time. This shows that a state of equilibrium is attained. For any pure liquid at atmospheric pressure 1.013 bar, the temperature at which the liquid and vapors are at equilibrium is called the boiling point of the liquid. Solid vapor equilibrium. Let us consider a system where a solid sublimes to vapor phase. When solid iodine is placed in a closed vessel, the vessel gets filled up with violet vapor after some time. The intensity of the color increases with time. We find that after a certain time, the intensity of color becomes constant, and at this stage, equilibrium is attained. Hence, solid iodine sublimes to give iodine vapor, and the iodine vapor condenses to give solid iodine. Thus, equilibrium is established in the system.
In this video, we'll be learning about dissolution of solids in liquid and the equilibrium that is established. We'll be also seeing the equilibrium involving dissolution of gases in liquid. Thus, we'll be looking at two kinds of dissolutions, namely solids in liquids and gases in liquids.
Equilibrium involving dissolution of solids in liquids. It is not possible to dissolve any amount of a solute in a given amount of solvent. For example, when we add sugar to water, the crystals of sugar keep on dissolving into the solution in the beginning. But after some time, no more of sugar dissolves. A solution in which no more solute can be dissolved is called a saturated solution. In a saturated solution, a dynamic equilibrium exists between the molecules of sugar in the solid state and the molecules of sugar in solution. Thus, a balance between the two rates, that is, the rate of dissolution of sugar and the rate of crystallization of sugar, is established. The dynamic nature of equilibrium can be demonstrated by adding radioactive sugar into a saturated solution of non-radioactive sugar. It is observed that the solution and rest of the non-radioactive sugar also become radioactive. This shows that even at equilibrium, the process of dissolution and precipitation are taking place. This means that equilibrium is dynamic in nature. Equilibrium involving dissolution of gases in liquids. The gases can also be dissolved in suitable liquids. At a given temperature, a liquid can dissolve on a certain definite mass of the gas. This suggests that a state of equilibrium exists between molecules in the gaseous state and the molecules dissolved in the liquid. For example, when carbon dioxide is dissolved in soda water under high pressure, the given equilibrium exists. At equilibrium, the rate at which the gas molecules pass into the solution becomes equal to the rate at which the dissolved gas molecules come back into the gaseous phase. The solubility of a gas in liquid depends on the pressure. The effect of pressure on the solubility of a gas in a liquid is given by Henry's law. This law states that the mass of a gas that dissolves in a given mass of a solvent at constant temperature is proportional to the pressure of the gas at equilibrium with the solution, provided the gas does not undergo any chemical change during the formation of a solution. That is, M is proportional to P or M is equal to Kp, where M is the mass of a gas, P is the pressure of the gas at equilibrium with the solution, and K is the proportionality constant.
In this video, we'll be learning about some general characteristics of equilibria, which involves certain physical processes.
General characteristics of equilibria involving physical processes. Let us now briefly discuss the characteristics of equilibria involving physical processes. The system has to be closed. Both the opposing processes occur at the same rate, and there is a dynamic but stable condition. The measurable properties of the system remain constant. When equilibrium is attained for a physical process, there exists an expression involving concentration of reacting substances which reaches a constant value at a given temperature. The magnitude of the constant value of the concentration-related expression is an indication of the extent to which the reaction proceeds before reaching equilibrium.
Today, in this video, we'll be learning about equilibrium in chemical processes. As we have seen that in earlier videos, we have learned about characteristic of equilibrium in physical process. In this video, we'll be learning about equilibrium in chemical process. We'll also learn about law of chemical equilibrium and what is equilibrium constant.
Equilibrium in chemical processes. A large number of chemical reactions do not go to completion and attain a state of equilibrium after some time. The state of equilibrium involving a chemical system is referred to as chemical equilibrium. Consider a general reversible reaction. In the initial stage, the concentrations of A and B are very high and that of C and D are very low. As the reaction proceeds, the amount of A and B becomes less, while that of C and D increases. At a particular time, under specified conditions in closed system, the rate of forward reaction becomes less and becomes equal to the rate of backward reaction. At this state, the reaction does not stop. Both forward and backward reactions take place simultaneously with equal magnitude, and reactions seem to be at a standstill. At this time, the concentration of reactants A and B and the concentration of products C and D are constant. This state of chemical system is called chemical equilibrium. Graphical representation of this reaction has been illustrated in the given plot. Let us consider the combination of hydrogen and iodine in a closed glass container. At first, the intense color can be observed due to the evolution of a large amount of HI. After a while, the color diminishes. This is due to the decomposition of HI to give back H2 and I2. At a particular instant, there will be neither diminishing of color nor increase in color. This shows that as much hydrogen and iodine combine to form HI in a particular rate, an equivalent amount of HI decomposes in the same rate to give back hydrogen and iodine. The given graph illustrates the reaction between hydrogen and iodine to give hydrogen iodide. Chemical equilibrium in the reaction can be attained from either direction. Law of chemical equilibrium and equilibrium constant. On the basis of experimental studies, it was proposed that the concentrations in an equilibrium mixture are related by the given equilibrium equation, where Kc is the equilibrium constant and the expression on the right side is called the equilibrium constant expression. This relationship is called the law of mass action or the law of chemical equilibrium. It states that at constant temperature, the rate of a chemical reaction is directly proportional to the product of the molar concentrations of reacting species, with each concentration term raised to the power equal to the numerical coefficient of that species in the chemical equation representing the chemical change. For example, the equilibrium constant for the combination of hydrogen and iodine is determined by the given equation. The equilibrium constant for the reverse reaction is the inverse of the equilibrium constant for the reaction in the forward direction. What will be the equilibrium constant for the given equation? The equilibrium constant for the equation is determined by the given expression. Relations between the equilibrium constants for the general reactions and their multiples are shown in the given table.
In this video, we will be learning about different types of equilibria, such as homogeneous equilibria, heterogeneous equilibria, and also we will be seeing the application of equilibrium constant.
Homogeneous equilibria. The equilibria in which all the substances are present in the same phase are known as homogeneous equilibria. For example, in the given gaseous reaction, the reactants and products are in the homogeneous phase. Let us find the equilibrium constant for the given homogeneous reaction. We know that the ideal gas equation is given by PV is equal to nRT. It implies P is equal to N over VRT. Here P is the pressure in Pascal, N is the number of moles of the gas, V is the volume in meter cube, and T is the temperature in Kelvin. If concentration C is in moles per liter or moles per meter cube and P is in bar, then P is equal to CRT. We can also say that pressure is equal to the product of the concentration of gas, universal gas constant, and temperature. At constant temperature, the pressure of the gas is proportional to its concentration. The equilibrium constant for the given equation is expressed by the given relation. The pressure of ammonia, nitrogen, and hydrogen gases are given by the expressions shown on the screen according to the ideal gas equation. Therefore, the expression for the equilibrium constant in terms of pressures of gases is given by the relation as shown. Similarly, for a general reaction, we can deduce the relationship between the equilibrium constant expressed in concentrations of gases in moles per liter and the equilibrium constant expressed in pressures of gases in bar. In the expression, delta N denotes the number of moles of gaseous products minus the number of moles of gaseous reactants in the balanced chemical equation. Heterogeneous equilibria. Equilibrium in a system having more than one phase is called heterogeneous equilibrium. Thermal dissociation of calcium carbonate is an example of heterogeneous chemical equilibrium. The equilibrium constant for the given reaction is as shown. Since the concentrations of both solid calcium carbonate and solid calcium oxide are constant, therefore, the modified equilibrium constant for the thermal decomposition of calcium carbonate is determined by the given expression. This shows that at a particular temperature, there is a constant concentration or pressure of carbon dioxide in equilibrium with calcium oxide and calcium carbonate. Applications of equilibrium constants. There are three important applications of equilibrium constant. These are predicting the extent of a reaction on the basis of its magnitude, predicting the direction of the reaction, calculating equilibrium concentrations. Let us discuss these one by one. The value of equilibrium constant tells us about the extent to which the reactants are converted into the products before the equilibrium is attained. Larger the value of equilibrium constant, greater is the extent to which reactants are converted into products. On the other hand, if the value of equilibrium constant is small, it indicates that equilibrium is mainly in favor of reactants and that only a small fraction of the reactants is converted into products. The equilibrium constant helps in predicting the direction in which a given reaction will proceed at any stage. For this purpose, we calculate the reaction quotient Q. The reaction quotient QC is defined in the same way as the equilibrium constant Kc, except that the concentrations in QC are not necessarily the equilibrium values. Look at the expression of QC for a general reaction. If the reaction quotient QC is greater than the equilibrium constant Kc, the reaction will proceed in the direction of the reactants, while the reaction will proceed in the direction of the products if the reaction quotient is lesser than the equilibrium constant. In case of a problem in which we know the initial concentrations but do not know any of the equilibrium concentrations, the following steps can be followed. Step 1. Write the balanced equation for the reaction. Step 2. Under the balanced equation, make a table that lists for each substance involved in the reaction the initial concentration, the change in concentration on going to equilibrium, and the equilibrium concentration. In constructing the table, define X as the concentration in moles per liter of one of the substances that reacts on going to equilibrium. Then use the stoichiometry of the reaction to determine the concentrations of the other substances in terms of X. Step 3. Substitute the equilibrium concentrations into the equilibrium equation for the reaction and solve for X. Step 4. Calculate the equilibrium concentrations from the calculated value of X. Step 5. Check results by substituting them into the equilibrium equation.